Chapter 3.1, Extrema on an Interval. Day 1, the Extreme Value Theorem. What is an extrema? First off, we need to have a function that is defined on an interval, a closed interval, well, actually interval, containing the point C, so x equals c. F of c is the minimum of the function on the interval if it's less than or equal to every value in the interval. That should be an f right here. F of c is a maximum if it is greater than or equal to every every f value in the interval of f. All right. So a minimum is the lowest point, and a maximum is the highest point. Right? And we go about it several ways finding extrema. We can talk about absolute extrema or relative extrema. Now when we say an absolute, it is the highest or lowest value on the entire interval. So if we're going all real numbers, it is the highest value possible, or the lowest value possible. All right? When we go a relative extrema, it is the highest or lowest value in the vicinity. So for example, it is a relative high or relative max if it is higher than the point on the left and higher than the point on the right, then it is a relative max. All right? So for example, a parabola has an absolute maximum right here. If we have a cubic right here, that is a relative max, because on the left is lower and on the right is lower. But over here, to the extreme left, it's higher. But in the general vicinity, to the left and to the right, it is a relative max. All right. Two examples of extreme. We got a cubic we just talked about, and then we have something else. What are the extrema here? Well, right here, this is a relative max. This is a relative min. And this is an absolute max. What can we say about the derivative at each extrema? Well, right here on the cubic, the tangent line is horizontal, so we can say here that f prime is 0. On the minimum, or the relative min on our cubic, again, it's a horizontal tangent, so f prime is also equal 0. Here it's a cusp, a sharp turn, and when we have a sharp turn, our derivative is undefined. So the derivative at each extreme, the derivative is either 0 or undefined. Okay. That's what happens at extrema. Our derivatives are going to be 0 or undefined. And that's on all real numbers, if their interval is all real numbers. All right, and a property of extrema is the derivative is 0 or undefined. And we'll use that to help us find extreme values. All right, and that brings us to the extreme value theorem, which is another existence theorem, the other existence theorem being the intermediate value theorem. Intermediate value theorem finds around a point. Extreme value theorem finds that there is a maximum point. And the conditions to use the extreme value theorem is our function is continuous on a closed interval. If that is true, we have a function continuous on a closed interval, it is guaranteed that there is a max and a min. All right? You think about it, we have ourselves a function on a closed interval. It's got to be continuous. So say from here to here, connect the dots however we want. There's always going to be a lowest and a highest point because we don't pick up our pencil. All right. Steps to finding extrema on an interval. Okay, and this is for a closed interval to apply the extreme value theorem. Okay, find the numbers that match the properties. These are called critical numbers. So again, make sure f prime equals 0 or is undefined. Those are our critical numbers. Okay, evaluate the function at each critical number. Evaluate the function at each endpoint, and the lowest of these is the minimum, and the greatest is the maximum. Because it's continuous, that is true. All right, so let's try it. Find the extrema of f of x on the interval from -1 to 2. First off, it must be continuous, and because it's a polynomial, it is, so we're good. So we're going to find our derivative so we can find our extreme values, or our critical numbers. All right, so our derivative is 12x to the third minus 12x squared. We'll set that equal to 0. We'll factor out 12x squared. We got x minus 1, so our critical numbers are 0 or 1. And on our interval, -1 to 2, we need to check our critical numbers and our endpoints. And I'm going to use the graphing calculator as an aid to do this. All right, so our function is 3x to the fourth minus 4x cubed. And then we'll check these values in a table. I'm going to go second table set to make sure I got it independent on ask. Then I can go to my function, my table. I'll clear out what's in there. I'm going to find f of 0 real quickly. F of 1. F of -1. And f of 2. Okay, and then using my table, I can very quickly see that 16 is the max, and it occurs at f of 2. So f of 2 equals 16 is the max. And the lowest value is -1, and it happens at 1. F of 1 equals -1. And because this is a closed interval, those are absolutes. Absolute minimum is -1, and the absolute maximum is 16. If we take a look at it graphically, I'll change my window to go from -1 to 2. My x scale can be 1. My y min, it says the minimum value is -1. Might as well put that in. My maximum value is 16. Put that in. If we graph it, we should get the whole graph to fit in the window. And we do. We can see our graph based on our max and min, and it fits. Let's try it again. Find the extrema of f of x on the interval, -1 to 3. It is continuous because we can take any number to the 2/3 power. So we will start, we'll find our derivative. F prime equals 2 minus, multiply 2/3 times 3 is 2x to the -1/3. We'll set that equal to 0. 2 minus 2 over the cube root of x. If we solve for x, we can divide both sides by 2 and flip. We get the cube root of x equals 1, so x equals 1. So we only need to check f of -1, f of 1, and f of 3. So again, let's use our calculator. We'll go to y, clear that out, and put in 2x minus 3 x to the 2/3. All right, let's go ahead and check our table out. We'll clear out our old values. And we just need to check -1, 1, and 3. So we can see our relative max, or our absolute max, sorry, because this is a closed interval. Our max is at 3, and it's -0.240. And our min is at -1, and it's -5. Okay, one more example. We'll take our derivative here. Is this continuous? Well, there's a discontinuity at 2, but is 2 in our interval? No, it's not. So we're good to go. We'll do h prime of t equals bottom, derivative of the top minus top, derivative of the bottom, over bottom squared. The top simplifies to -2. The bottom is t minus 2 squared. What makes a fraction 0? Well, if the top is 0, and -2 is never 0, so that's not a possibility. How do we get undefined? If the bottom's 0, the bottom's 0 at 2, which is not in an interval. So that's okay. So all we need to do is check 3 and check 5. And if we do this real quickly, t over t minus 2. Go to our table, and we just need to check 3 and 5. We can see the maximum is 3 at 3, and the minimum is 1 2/3 at 5. So in conclusion, the extreme value theorem, a function that is continuous on a closed interval has a maximum and a minimum. To find those extrema, first off, you must verify the function is continuous so that the extreme value theorem applies. Then you're going to find your derivative. Find where your derivative is 0 or undefined, and those are called critical numbers. And then you're going to check your critical numbers and the endpoints. The highest is the maximum, and the lowest is the minimum.